Hi. On every smartphone, tablet and computer, there is a scientific calculator where you can see the names of some of the elementary functions like sine, cosine, tangent and many others. For example, we can calculate the sine of any number obtaining a value like this. But how does it work? If you have ever wondered, this video is for you. Let's try to understand. We have to start with the tangent line. This is the line with the equation y equal fx star plus f prime x star times x minus x star at some point x star where the function f is differentiable. Among all the possible lines passing through the point x star fx star, the tangent is the one that best approximates the graph of the function near the point x star. This is expressed by the property that the gap between the function and the tangent line is as small as possible, going to zero faster than x minus x star, whereas for any other line, this gap goes to zero as x minus x star. Equivalently, near point x star, f of x can be written as the sum of a first-degree polynomial plus a remainder which is negligible compared to the polynomial. Now, the fact that we can use a first-degree polynomial to calculate f of x makes the operation easily codifiable for a machine capable of performing arithmetic operations. Now, under what condition is it possible to improve this type of approximation? To do so, we need to understand what's inside the remainder, which is the little o of x minus x star. For example, we might expect a quadratic contribution in x minus x star, and a new correction that will be negligible with respect to this quadratic contribution, so it should be smaller than x minus x star squared. So the question is, under what assumptions is this true? And how can we determine the coefficient C2? Well, we can expect that the answer is somehow related to the curvature of f, because just a straight line is straight and the quadratic term is parabolic. So, in other words, we expect that this has to do with the second derivative of f at point x star. And this is exactly what happens. In fact, we assume that the second derivative at point x star exists. If we want that f of x can be written as this second degree polynomial plus this remainder, this is equivalent of saying that the gap between f and the polynomial related to x minus x star squared, so doing the ratio between these two quantities, this ratio goes to zero when x goes to x star, because this is the definition of what is a little o. Now, if we observe what happens when x goes to x star, we realize that since the function f is differentiable, we have this assumption because we are assuming that there is a tangent line, for example, the function f is also continuous. So when x goes to x star, f of x goes to f of x star, and this makes this difference going to zero. The other two terms here, they both go to zero when x goes to x star, so the numerator of this fraction goes to zero, as well as the denominator. So we have a 0 over 0 indeterminate form, and therefore we may try to compute the limit by using the Hopital rule. Now, computing the derivative of the numerator with respect to x, remind that this x star is just freezed, is a fixed, while the variable is x, we have f prime of x minus, this is a constant, so it is washed out by the derivative. Here we have constant times x minus x star, so the derivative will give just a constant, f prime x star. And here we have c2 x minus x star squared. So 2x2 x minus x star divided by 2x minus x star. Now again, this is a 0 over 0 indeterminate form because when x goes to x star, since we are assuming that f second at x star exists, f second is the derivative of f prime. So in particular, f prime is differentiable at x star, and therefore it is continuous. This quantity goes to f prime of x star. So this gap goes to 0, while this goes to 0, numerator goes to 0, denominator clearly goes to 0. But now to compute this limit, we don't need to invoke again the Hospital rule. We just need to reorganize the expression, writing 1/2 in front of everything, the limit. You see the white expression is just this ratio, which is the incremental ratio for the derivative of f prime, which is exactly f second at point x star. Minus, when we subtract this and we divide by x minus x star, we see that we get just a constant minus 2c2. So when we do the limit under this assumption, we get 1/2 f second at point x star minus 2c2. Now, if we want that this quantity be equal to 0, we need that 2c2 be equal to this f second x star. So at once we have that this limit is 0, so the polynomial approximation holds when f second of x star exists, and this is the shape of this second degree polynomial. We call this the second order Taylor polynomial centered at point x star. For example, if the function f is sine of x and the center is pi half, we want to compute the Taylor polynomial, which is this one. You see that we need to compute f, f prime, and f second at point pi half. Now, f is sine x. When we evaluate at pi half, we get sine of pi half is 1. F prime is cosine, the derivative of sine. So the value of f prime at point pi half is cosine of pi half, which is 0. And the second derivative of f, which is the derivative of f prime, so it is minus sine x now, this has value at pi half equal to minus 1. So this yields this polynomial, p2 equal 1 minus 1/2. There is not the first order term because the coefficient is 0 here. So 1 minus 1/2 x minus pi half squared. Here you can see the graphical representation of this formula. We have sine, which is the orange line here, and the green line, which is the parabola, 1 minus 1/2 x minus pi half squared. As you can see, around point pi half, the parabola overlaps the sine. So this means that the two functions are more or less the same, so we could use the polynomial to compute sine in a neighborhood of pi half. At this point, it's natural to ask if it's possible to further improve the approximation. For example, can we say that a function f can be written as the nth degree polynomial plus a reminder that must be now negligible with respect to the polynomial, and this will mean that it is a little order of x minus x star to the power n. Now, this is well possible, and the answer is provided by this important theorem, which says, suppose we have a function f defined in a neighborhood of some point x star, for which there are a certain number of derivatives. So derivative of the derivative, and then we differentiate a certain number of times until order n on the neighborhood ix star. Then the function f of x can be written as polynomial Pn of x plus remainder, which is little o of x minus x star, where the polynomial has this shape. It is the sum for k going from 0 to n of these powers, x minus x star to power k, and the coefficient is the fraction, a numerator, the kth derivative of f at point x star, so the center, divided by the factorial of k. Now, this nice formula has an important special case, which is called the Maclaurin formula. Maclaurin formula is just Taylor formula centered at x equals 0. So you get that x star becomes 0 and x minus x star becomes just x. So we get this. For example, if we take the function f of x equal e to x, the exponential, the Maclaurin formula is this one in general. So we have to compute the values of the derivatives of f at point 0. So f is the exponential, the value of f at 0 is 1. When we differentiate, we get again the exponential, because the derivative of the exponential is the exponential. And therefore, also the first derivative of f at point 0 will be 1. But then when we differentiate f prime to get f second, we again get e to x. And this happens for all the remaining derivatives. So we may say that for every k, the kth derivative of f is always e to x, and therefore the kth derivative at 0 is always equal to 1. This means that all these numbers are 1, and that's why we get this formula. This is actually many formulas because we have a formula for n equal 1, so where we stop at power x to 1. So we have just two terms, the degree 0 term, x to 0 over 0 factorial, which is just 1, plus x to 1 divided 1 factorial, which is just x, plus the remainder, which is O of x. If we want to have a better approximation, we add a term, this second degree term, so we add to the previous expansion x squared divided 2 factorial, so x squared divided 2, plus now the little o becomes a little o of the last power, so x squared. If we want to arrive until order 3, we have to add x cubed divided 3 factorial, which is x cubed divided 6, and now the little o becomes even smaller, o of x cubed, and so on. You can graphically see what happens. Here we have the plot of the exponential, and in green the plot of the polynomial. That's the first degree polynomial, the second, the third, the fourth, the fifth, the sixth. You see that for this case, on this interval, we do not distinguish anymore the exponential from the polynomial. So we may use this 6th degree polynomial to compute e to x in this range. Nice. Now, Maclaurin approximations are important for computing limits, to discuss convergence for numerical series and integrals, and in general, in many questions where the asymptotic behavior of a function matters. Well, now it's your turn. I suggest you to practice both formulas, particularly Maclaurin formulas, computing some expansions as those proposed here. And to go on a deeper level, I just propose you to solve this general problem. Good luck, and may the wind be always at your back.